Hello, in this session we are going to talk a little bit about graphing rational functions. My name is Melody Elrod and I'm a private tutor based in Tennessee who also tutors online. You can find out more about me and what I do at www.melodyelrod.com. But for now, let's go ahead and talk a little bit about graphing rational functions. To begin talking about graphing rational functions, we need to talk about the things that we need to have in our arsenal in order to graph. We need to find, first of all, the vertical asymptotes, the horizontal asymptotes, the x-intercepts, and the y-intercepts, as well as sometimes maybe a few other points. So these 5 things are going to help us to graph a rational function. Let's take, for example, f of x is equal to 2 times x squared minus 9 over x squared minus 4. The first step to graphing any rational expression, as far as I'm concerned anyway, is to factor everything. Because through the factors, we reveal a lot of stuff. So we could rewrite f of x as 2 times x minus 3 times x plus 3 divided by x plus 2 times x minus 2. We want to be on the lookout for factors that might cancel from the top and the bottom. In this particular case, they do not, so that tells us we can keep going. The second step is finding those vertical asymptotes. I'm not going to write out vertical asymptote every time because it's really long, so I'm just going to use VA to substitute for that. Vertical asymptotes happen where we have numbers outside the domain. For a rational expression, that means where the denominator is equal to 0. So if we set the denominator equal to 0, that should reveal our vertical asymptotes. So if we take x plus 2 times x minus 2, and we set that equal to 0, that leads us to vertical asymptotes at -2 and at +2. So there are vertical asymptotes. Awesome. Step 3, finding those horizontal asymptotes. Now, horizontal asymptotes have to do with the limit as x approaches infinity. Now, if that sounds like really fancy talk to you, if your teacher hasn't talked to you a lot about limits, they probably talk to you more about end behavior. That's another way to talk about limits, but it all comes from the idea of a limit. In this particular case, whatever this is headed towards, whatever the limit is at infinity, that's going to be your horizontal asymptote. So let's investigate a little bit further. I can find the limit as x approaches infinity, and we'll talk a little bit more about what a limit is as we go, of the function. Now, with this kind of work, what we're asking ourselves, a limit at infinity asks us this question. What happens when x gets big? As in really big, as in big, big, huge, millions and trillions big, massive. Because what we're doing is we're headed towards infinity. Okay, what that means is as we're headed towards infinity, the x squareds have all the power and the 9s have nothing. Think about it this way, 1,000,000 squared minus 9. Still pretty much 1,000,000 squared, right? So there's not a whole lot of power in this -9 once we get into the millions and trillions. And so what I like to do is to think about it this way. Take all this stuff off so I'll have room to do my next step. So what I like to think about is this. If we remove the power of the rest of them, so let's multiply out so that we can do what we need to do. Let's go ahead and multiply out the numerator, 2x squared minus 18 divided by x squared minus 4. I like to remove the power of all of these terms by dividing by the biggest of those terms. Let's divide by the largest power. And that looks like this. I carry my limit notation, by the way, constantly, because I'm still talking about limits, and I don't want to forget that. I take away the power by doing this. By multiplying by the same thing top and bottom, I'm essentially multiplying by 1. Anything divided by itself is 1, and so that's totally legal. And I get something that looks kind of like this. The limit, as x approaches infinity, of 2x squared divided by x squared is 2. 18 divided by x squared is 18 over x squared. And x squared over x squared is 1 minus 4 over x squared. And then again, I ask myself this question: what happens when x gets really, really big? So consider this fraction. When x is huge, 18 over 10 squared, 18 over 100 squared, 18 over 1,000 squared, 18 over 1,000,000 squared, what's happening to those fractions is as the denominator gets huge, the fraction itself gets very, very small. In fact, it gets so small that it becomes almost nothing. These have no value at the millions and trillions. And so what we're left with is just 2 over 1, or just 2. So our horizontal asymptote is y equals 2. Okay, the next thing that I want to look at are my x and y intercepts. And remember that since this is a video, if you need to rewind, replay anything that seems a little bit fuzzy, please do that. So step 4, x-intercept and y-intercept. And I like to look at them at the same time. In fact, I'm going to spread them out a little bit so that I can do it kind of in columns. X-intercepts all lie on the x-axis, which means that they have one thing in common, and that is that y is 0. So if I take my f of x value and set it equal to 0, then I have 0 is equal to 2 times x squared, we call that x plus 3x minus 3, over x plus 2x minus 2. Let me double check myself and make sure I've still got the right function in my head. Yes. Okay, everything's cool. If I multiply both sides by this x plus 2x minus 2 business, if I multiply both sides by x plus 2x minus 2, it cancels it off the right side, and anything times 0 is still 0. So I have 0 equals 2 times x plus 3, x minus 3. And so that gives me zeros at -3 and at 3. And why does it not give me 1 at 2? Well, because if I set 2 equal to 0, that's just not true. That's just false. 2 is not 0. And so therefore, there's not 1 here. We disregard this. All right. So we have x-intercepts at -3, 0 and at 3, 0. Okay. Y-intercepts. Let's talk about y-intercepts. Y-intercepts happen where x is 0 because they all lie on the y-axis, and the only thing that they all have in common is that x is 0. So I take f of 0, and I find 2 times 0 minus 9 over 0 minus 4, and that gives me -18 over -4, or positive 9/2, about 4.5, right? Actually, exactly 4.5. So my y-intercept is 0, 4.5, or 0, 4.5. So now I have a lot of information. I know where my vertical asymptotes are. I know where my horizontal asymptote is. I know where my x-intercepts and my y-intercept are. And this is going to help me to go ahead and get started graphing. So what I do before I do that whole, well, graph some more if you need to, is I put what I have on the xy plane. I go ahead and start graphing some of the things I know are true. Okay, so here's my graph. I know that I have a vertical asymptote at, let's see, where were my vertical asymptotes? My vertical asymptotes were at 2 and -2. So let's put those on the graph. So I have one here, and I have one here. And to make them look like asymptotes, I like to dash them. This particular software is not really great for dashing things. So I'm gonna make this work a little bit better. Just dash them through. I also know that I have a horizontal asymptote. And where was my horizontal asymptote? Well, again, my horizontal asymptote was at where? Horizontal asymptote was at y=2. So let's take that back off. Okay, so y=2 is going to give me a horizontal asymptote, which is going to be here. Okay, again, I'd like to dash that. So I dash it. Dink, 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 dink. All right, I got some more information coming. Okay, I also had x-intercepts at, I had x-intercepts at 3 and -3 and a y-intercept at 4.5. So y-intercepts or x-intercepts at 3 and -3. So one here and one here. And a y-intercept at 4.5. That gives me some information. Now, vertical asymptotes are tricky things. Because they're outside the domain, you know that you can't cross it. Okay, I cannot go across. I couldn't take this point and connect it to this point. That won't work because that would cause me to cross a place in the domain that does not exist. Instead, what I know is this. I know that my end behavior is going to follow the horizontal asymptote. And I know that my behavior towards the graph is going to go this way. Okay, it's not going to bounce off. Unlikely for it to bounce off. If we wanted to be really sure, we could test the point 2.5 and just see what that value is. More than likely it's negative, so I'm gonna stick with the negative for now. And the same thing happens over here. We're bounded to the right by this vertical asymptote. We're bounded above by this horizontal asymptote. And so we get this general behavior for the graph. In the middle, I've got some options. Whereas I cannot cross a vertical asymptote, I can cross a horizontal asymptote. It's not illegal. Now, I do know a couple of things though. First of all, I know that this can't go down. Why can't it go down? In order for it to drop, in order for it to decrease at that point, it would have to cross the x-axis. I've already established that it only crosses the x-axis here and here. That was part of my math. I already did that. So I know it can't cross the x-axis again. So that line does not go down, which means it has to go up. And the same thing is true on the other side. It can't go down, so it's got to go up. Okay, and now we have a nice graph. Now, in this particular one, one of the things I said that we might need are some extra points. In this particular case, we didn't need any extra points. In fact, in this particular case, we have all of the information that we need simply because we have the x-intercepts and the y-intercept. They gave us all the information that we needed. Sometimes, though, we might need a little clarification. Is it below the horizontal asymptote or above it? Is it going to rise or is it going to fall? And those things can be found out really easily by just plugging in a point. For example, if we wanted to know what happens at x=5, for example, let me change colors. So at x=5, what's happening at x=5? Well, I could just very simply plug it back in. I could say, okay, well, what is f of 5? Well, it would be 2 times 5 squared minus 9 over 5 squared minus 4. So that would be 2 times 25 minus 9 is 16. So 2 times 16 over 25 minus 4, which is 21. So this is some positive value. 32 divided by 21, it's bigger than 1, right? So it's about here-ish, okay, which is about where we were. So this is great. This is good. Okay, that gives us the information that we needed. But you can plug in test points to figure out what you don't have if you need to do that. Okay, so this has solved our graph. This has graphed this function for us. Okay, I encourage you to take some time to look at some other examples and to see if you can graph them using this same method. And remember, what we're doing is we are finding vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts, and then if we need to, so we graph all of this, and then if we need to, we find some other points if it's necessary. All right, so hopefully this has been helpful to you. And if I can be of assistance to you in any way, feel free to drop me a line. You can find my contact information at melodyelrod.com. Have a great night.